the correlation function C of n, the point was I had a infinite or rather a finite series which read 1 minus nc2 e to the power minus plus 2j kt plus n. No, this is nc4. Plus nc4 e to the power, this was 4. Now, the 2 is 2 with a minus sign, the plus is the e to the power minus 4j over kt, and so on. And downstairs one had 1 all plus e to the power minus 2j. Right. So that's the common ratio is e to the power minus 2j kt. So that was the error. It started with the nc1, then nc2, and then it goes, and it is nc1, nc2, and that's minus 2 kg, right? All plus here. My alternatively plus and minus over here as the one flip and 2 flips and so on. Even and odd. So these were the even flips. If I have two of the endpoints up and up, then the point is I would have to have at least 2 flips to get going. If I have the endpoints up and down, just 1 flip would do. So up and down here means -1. That is why the minus over here, and the plus over here, because that corresponds to this and so on. That's the way it goes. So the common ratio is this. So the binomial expansion that I'm looking at is e to the power minus 2j over kt to the power n over here, as you can easily compare. I mean, that's, and it is e to the power minus 2j over kt to the power n over here. So it is tan hyperbolic e to the power j over kt, right? I mean, it's take out it's 1 minus e to the power minus 2j over kt. So this is e to the power if I take out a minus j, then this is a e to the power j over kt minus e to the power minus j over kt divided by e to the power j over kt plus e to the power minus j over kt, right? So that's the tan hyperbolic j over kt to the power n with sorry, it's tan hyperbolic j over kt. What to the kunta? Beta kisher? Oh, acha. So that's all right. So that's what the answer should have been, that it is tan hyperbolic j over kt to the power n. And now if it is at very low temperatures, this is very high. So it is like 1 minus e to the power minus 2j over kt, 1 plus e to the power minus 2j over kt to the power n, and that is like 1 minus 2n e to the power minus 2j over kt. So 1 minus roughly, so this is very small, so that's 1 minus 2n. The correlation function looks like e to the power minus n over xi, which is equal to 1 minus n over xi. So xi is equal to e to the power 2j over kt over t. So that's the correlation leg. And now things are, I mean, that had to be because the susceptibility is related to correlation functions, as we know that it is the correlation function and the dimensionality integral over the DDR in a d-dimensional space. That is what gives me the susceptibility. This is the general answer, connection between thermodynamics and the correlation function. The C of R over here goes like e to the power minus 2j. The susceptibility goes like e to the power 2j over kt. So the correlation function, which is like e to the power minus r over xi ddr, has to go scale like xi to the power d, and xi, so in d equal to 1, chi should have the same scaling as xi. So it is chi is e to the power 2j over kt. Xi is also e to the power 2j over kt. So that was essential. So that's the point over here, that if the correlation function decays like e to the power minus r over xi, the scaling of this is like xi to the power d, and that's what the, and therefore. So that's cleared up. So that was necessary. So all right. So what, with this one-dimensional Ising model, which I can solve exactly in very many ways. I have this answer that we did it essentially by the transfer matrix. That is what we chose to do over here. And we have chi go as e to the power 2j over kt. The correlation length goes as also e to the power 2j kt. Transition temperature is T equal to 0, and that's the behavior near the transition. This is behavior near T equal to 0. So that's what I want to look at this in a slightly different way. So, all right, I mean, we did the transfer matrix, which is a pretty general way of doing problems of this kind. Solve it up to a point and then ask what happens if I go one more step and correlate the Zn plus 1 with the Zn. So that's what the transfer matrix was all about. Let me do a very different kind of thing. I have a Z to evaluate, which is a sum over beta j si plus 1. So I equal to, let's say, from 1 to n. minus. So I ask the question, so that's what I'll do it for h equal to 0, which makes life easier, the algebra simpler, but no. So I ask the question that, well, let me do this sum over only the over the even spins. So I have spins. So I'm sitting. These are the sites. 1, 2, 3, so on. And let's say I do the sum over all the even chaps over here. That is, I do the this is sorry, I equal to 1 to n sum over all configurations. That it's a sum over all configurations. Chap I. So I want to do it over all the configurations. I want to do the spins, all configurations, meaning the spin at every site and each one of them up, down, independent of each other. So 2 and now I'm going to do it over 2, 4, 6 and so on. So all right, I want do Z over only the even spins. So I'm looking at typically e to the power beta. So let's say spin 2. So it is S21 plus S23. Right? So this is the part that I want to focus on. So it is for 2, it would be S21 plus S23. Come to 4, it is going to be beta S43 plus S45. And so in between, I mean, so I pick up the spin, I pick up spin 2 and want to do a sum over these. There is S13, S13 is not there. I mean, it started out with S12, S23, S and so 24 and so on. So I'm looking at spin 2, so this one over here, and I want to do the tracing over this and this. And therefore, what I expect if I do this over here, that, sorry, it's not the, I want to do the tracing over this chap over here. So that's the, so where I do the trace over this, I expect that it would reduce to something like S1, S3, e to the power something times S1, S3. So S21, S23, I do the trace over S2. So S2 up and S2 down, and there would be different all the configurations, which is S2 up, sum over S2 up, S2 equal to +1 and S2 equal to -1. So 2 terms over there, and I expect the net result would be that it is some S13. Similarly, I do this over 4, and I expect that the answer would be something times the same thing, whatever I had over here, times S3, S5. So if this is done, then you see I have reduced this problem from one Ising model to another Ising model. The difference between the two problems is that over here, the lattice spacing was, let's say, A, and over here, the spacing has become 2A. So you have moved this from, you have just changed the lattice spacing in the, so all right, that's, and then I can go on doing this if I have a, at the end of the day, if I can write things cleanly, then I need to do it only once. And then I can say that, all right, next time I have S1, S3, I'll remove the S3 and I'll get S1, S5. And eventually I will just be reduced to S1 and this, and that I know what the answer is. All right. Yeah. So I do the trace over 2 and 2, and I expect that it comes to S1, S3. Do it over 4, it's S3, S5, and so on. So at the next step, I will do it over 3, and then do it over 7, and so on. And I will have S1, S5, and so on. And eventually, it will just be S1 and the last one. All right. So that's the. Now, why in the, all right, let's see at least whether I can do it. How do I expect to do this thing? So I know that if I do the sum over S2 equal to plus minus 1, e to the power beta j, S1, S2, plus S2, S3, then the answer is certainly e to the power beta j, and S2 equal to 1 means S1 plus S3, and plus e to the power minus beta j, S1 plus S3. That's the answer. Now you can say, I'm disappointed. It doesn't look like this, but I'll make it look like that. I want it to look like this. So I'll say, look, don't worry. Let me just write it as some constant c e to the power some constant j1 and in e times s1 s3. All right. So I'll take it and say, I'll write it that, don't worry, I'll write it like c e to the power c exponential some, I don't know the constant c and j1, but I say that I'm going to find it. There exists a c and j1 for which I can write this as this. All right. So question is, how do I find it? What you are interested in, the only thing you are interested in this world is that what happens to this answer if S1 and S3 are parallel and if S1 and S3 are antiparallel. right? That's your that's your interest. So all right, if that is your interest, then you want to make sure that that works. And so I'll say S1, I'll take S1 equal to S3 equal to 1. And then notice that -1 and 1 is not going to make a diff. I mean, whether I say it is equal to 1, it doesn't matter. So e to the power 2 beta j plus e to the power minus 2 beta j is equal to c e to the power j prime j1. And what if S1 is equal to minus S3 is equal to 1? So spins are antiparallel. In that case, it is going to be your e to the power 0 and another 0. So it is 2. 2 is equal to c times e to the power minus j1. You divide by these two and you get e to the power 2j1 is equal to, so this divided by that is equal to half e to the power 2 beta j plus e to the power minus 2 beta j1, which is equal to cos hyperbolic 2 beta j. So given j, this is my j1, and what is c? C is equal to C can be obtained, let's say, from here. E to the power j1. So C is equal to 2j1. No, C is equal to 2 e to the power j1 is equal to, this is 2, and e to the power j1 is square root. So square root of cos hyperbolic 2 beta j. Right? So I know what C is. So I know exactly what to do. That if I at the thing which I'm looking at, after I have done it for this, I have done it for this, and so on, I'm looking at e to the power some j1, e to the power j1, and it is S2, sorry, S1, S3, there is a beta j1, S1, S3 plus S3, S5, and so on, whichever. And there is C, a constant, this e to the power beta j1. I'm writing, just want to get the C in. This is equal to 2 e to the power. I have found the C. I have done the partition function. I have done this part of it, and I'm reduced to getting e to the power. So what I evaluated was, I evaluated this e to the power over this configuration, and I had written it at this as c e to the power j1. This is my so there will be, each one of them will be a factor c, and how many of them roughly there are going to be n over for each one of them. I'll be picking up a factor of c. So if there are n sites, I would be picking up n over 2. So all right. So I have another Ising problem, right? I started with one Ising problem, which was this, and I now have another Ising problem, which is given by this, and my J1 equal to half log cos hyperbolic. Got it? So now that I know this, I'll say I'll do it again. So I'll do it again, and I will get J1 will go to some J2, which is equal to half log cos hyperbolic 2 beta J1. So where will I stop? I will stop when this, so this is a recursion relation. It's Jn plus 1 is half log cos 2 beta Jn. Right? So Jn plus 1 is half log cos hyperbolic 2 beta Jn. So I go on doing this, step 1 to step 2, step 2 to step 3, step 3 to step 4, and I'm removing more and more space. And every time the J is getting changed, you are picking up J with a coupling constant at the n plus 1th stage is related to the coupling constant. Huh? It's Kadanoff done in d equal to 1. So Jn plus 1 is half log cos hyperbolic 2 beta Jn. And what has been happening to the lattice spacing? The lattice spacing has been going from, the lattice spacing goes A to 2A to 2 square A and so on. All right. What happens to the correlation length? So suppose suppose you calculated the correlation length for this system, C is just a multiplicative constant. Every time you will be picking up a square root of it. Yeah, sure. So what's going on? The lattice spacing is changing. The correlation length is always in there is only one unit of length over here, which is the lattice spacing. Correlation length is something times the lattice spacing. If my lattice spacing doubles, A goes to 2A, means the correlation length goes to xi by 2. That if my correlation length previously in terms of is 10 lattice or 12, let's say 12 lattice spacings, now that you are in the new lattice, you are going to, the correlation length hasn't changed. I mean, it's just whatever it was. But now in terms of the new lattice spacing, it is simply the in units of the lattice spacing, it is now 6 lattice spacings instead of 12. So what changes? So see what is vital is that xi is equal to some, let's say, large number of some lattice spacing. I have carried out this procedure and removed some of the spins. My unit has changed, and now this correlation length that you had, you were saying that xi is equal to 16a, which is the original lattice spacing. But now in terms of the new lattice spacing, it is simply 8a prime. This has not changed. Mind you, that does not change. It is only in units of lattice spacing that you find that this correlation length has gone down in terms of, because when only 2 spins are left, the correlation length is just 1 lattice spacing, right? So eventually, I mean, this will just boil down to 1 lattice spacing. But now in the real system that you are looking at, in the real system, let's say it is 1. That is what you were supposed to compute. But what you have done is you have started removing, so gone from that system to another equivalent system to another equivalent system, and finally, at the end of the day, to a system where it is just 1 lattice spacing. Yeah. And a system with only 1 lattice, that Stat.Mech you can trivially do. And therefore, I mean, you have, I mean, all right, but the point is that what this is telling you is what am I interested in? I'm interested in a situation where it's t equal to tc. My interest is in t equal to tc, where the correlation length is infinitely big. And therefore, these scale changes don't matter to it. And that is the scale invariance of the critical point. How can a correlation length change? correlation length was, I mean, the system has correlation length. If it is you specify its temperature, specify everything, there is a definite correlation length. If it were to be measured in centimeters, if it is 100 centimeters, it always remains 100 centimeters. What you are doing is, in this process that we have outlined over here, you are not changing the definition of centimeters. You are changing the definition of what is a lattice spacing. Everything is in the unit is no longer the centimeter unit. The unit is a lattice spacing. And that is why this question, I mean, the fact that in units of lattice spacing, you are going further and further away from, I mean, if Xi was not infinite, but was 1,000 angstroms when you started, you can, 1,000 angstroms remains 1,000 angstroms. But the point is, by doing, in terms of the lattice spacing, which probably corresponds to 100 lattice spacings, that 100 lattice spacings is now changed to just one lattice space. Yes, right. Yeah. There you don't. So that's what the physics is. And therefore, this transition, this thing which I have written over here has to reflect the same physics. Get the point? So what is the same physics? The same physics is that here at the critical point, the correlation length, I mean, in this units of the lattice spacing, when it is actually infinitely big, you cannot change it by this transformation. Therefore, if this is eventually if you are at the critical point, that has to correspond to the fixed point of this transformation. So where is the critical point? The critical point is where, I mean, you are going on doing this recursion, but when you hit J star equal to half log cos hyperbolic 2 beta J star, that corresponds to your critical point. If you are sitting over there, you can't change. Right? So this successive recursion relation, what it is doing is that it is headed towards the criticality. That is, the Xi is going to become, the Xi essentially is going to become you are going away from the every time you do this, you are going away from the critical point, further away. But if you are, and you won't be able to go away if you are sitting at the critical point. So you start with any J star, which if you start with J star, you remain at J star. That's what. But you don't start at J star, you are going to go away from the critical point, and it's going to become. Yeah. Not? It's not stable. That's the whole idea. Absolutely right. That the fixed point corresponding to criticality has to be an unstable fixed point, because if this were to start If I were to start slightly away from there, I would have to go away along with. So the critical fixed point has to be an unstable fixed point in what would be the relevant variable. I mean, over here, there is just one variable, temperature. So if I start off temperature, then if it is a magnet with a magnetic field as well, then there are two. You have to sit at, it is T equal to Tc at H equal to 0. You can go away from criticality by switching on a magnetic field. You can go away from criticality by moving away from Tc. So in in presence of the magnetic field, you have to, I mean, you will have to play the same game with H over here. At criticality, it is the temperature reaches the fixed point. Similarly, the H also would have to reach a fixed point, which, I mean, would be for the magnet 0.
Sir, one thing.
Yeah.
That means that T going to 0, this unstable fixed point becomes a stable one.
Sure. Yeah. T equal to 0 is an unstable fixed point. Right. Which is what we'll see in a minute. Absolutely. Sure.
Okay.
Sure. So my recursion, absolutely, that's the point. This is the recursion relation. And here is the fixed point. Here is the fixed point. So what is the fixed point of this? What fixed point does it have? The fixed point is obviously going to be in, I mean, you write the other side over here, you are, what are you looking at is essentially cos hyperbolic, the fixed point looks like cos hyperbolic 2bj star is equal to e to the power 2. There should have been a beta somewhere, no? Lost it. It's in the recursion, should have been in the recursion here. It should have been a, sorry. I mean, trivially, all of them should have had it. All of them should have had it. So it is in e to the power 2 beta j star. And the only fixed point that this can have is j star equal to 0 or j star equal to infinity. The two fixed points. So j star equal to 0, this is 1. J star equal to 0, this is 1. It is and so j star equal to 0, yeah, and infinity, both of them infinitely big. Who cares? So infinity j star setting off to infinity, which is in fact a little funny fixed point, but anyway, I mean that it is right side and left side, both of them, and j star equal to 0. So that's the, those are the, so you have this situation.
Sir, why are we saying that the fixed points of this recursion relation correspond the T equal to Tc? That's the, why are we saying that this recursion relation, fixed points of this recursion relation gives the
Because that is where the whole physics says that unless it is xi equal to infinity, there cannot be any fixed point. So unless I start with, if I start with a xi which is, let's say, 1000 lattice spacings, or I mean 1024 lattice the next time around it is going to become 512, then 256, then 128, and so on. It is only if I start at the fixed point where xi is infinitely big, that is when, I mean, the system is physically, you cannot change the correlation length by rescaling anymore, and therefore the critical point which I identify with infinitely long correlation length is described only by the fixed point of this, because only if you stay at the fixed point, it is only if you are at the fixed point, only if you describe things in terms of the fixed point, it makes sense to say that if I'm there, I'm there. But if I'm not there and it's an unstable fixed point, then I go away from it. That is why. That's the. So it is the maths of this being connected to the physics of this. That the maths was that I went on increasing the lattice spacing. So lattice spacing increasing meant that in terms of that, if I write it as so many lattice spacings, then I'm just going on decreasing the correlation length in units of lattice spacing. And that will not be allowed only if I sit at the critical point. But as soon as I move slightly away, then every move will take me more and more further and further away. So that is the maths over here gets connected to the physics over here. So I need to check J star equal to 0. I mean, it should be an unstable fixed, better be an unstable fixed point. Yeah. J star equal to 0 is a fixed point, so it had better be. T equal to 0? I mean, it's actually beta J star equal. You have to be careful. I mean, it is this coupling constant. I mean, what is 0 is k equal to beta j. It's k equal to beta j. So over here it is, I mean, obviously so k equal to beta j, which is j by kt, and over here the thing is that it is actually the only way k becomes infinitely big is through, I mean, your t going to 0. The j is a property of the chain which does not change. Elsewhere, when we do, I mean, this is a feature of the finite of the one-dimensional problem, where, I mean, the only ordering is at t equal to 0. There is really no ordering at phi. But when it is a finite temperature ordering, then, I mean, one can talk about, I mean, the point is t can be left at Tc. I mean, if as we did for all the calculations that I was showing you before, that you just leave t equal to, I mean, the denominator over here is never significant. I mean, if I have a coupling constant which looks like j over kt, then for all finite transition temperatures, it is like j over ktc, and the game is in the j over here. The ordering is at t equal to 0. So Tc is 0. I mean, yeah. This corresponds to a TC of infinity. This corresponds to a TC 0. I mean, that is why this is a little pathological in the sense that it's, I mean, it's actually talking about a physical temperature. Elsewhere, when you talk about these theories like A phi square over 2 and so on, and A is equal to A0 T minus Tc, A is just left as a parameter over here. It is, I mean, you bring in a finite temperature when it's a transition at a finite temperature, the T minus, the A does get renormalized, but I mean, Tc is not, it is this T minus Tc which is the thing which is vital. Over here, it becomes actually that it is, I mean, then you are going to say that if I'm sitting exactly at Tc, then things are critical and the fixed point would, I mean, as we'll see very soon, but then, but over here, it is actually this T equal to 0. The T equal to 0 and T equal to 0. In some sense, because this is an exact theory and those are effective, I mean, sort of the phi square having this coefficient. But right now it is this. But as I said, I argued that J star equal to 0 is a legitimate fixed point. That if I'm going to sit over there, I will always sit over there. My temperature is infinity. Whatever I do, it's infinite lattice spacing. I'll sit at infinite lattice spacing. So, I mean, it's a legitimate candidate. So, how do I check? The recursion relation is as that's a fixed point, but the recursion relation is that cos hyperbolic 2 beta jn is equal to e to the power 2 beta jn plus 1. So you say jn is equal to, let's say, some j star plus a small delta n, in which you are going to, this is a small deviation, and you are going to small deviation, and you are going to linearize. So if it is about this, then this side over here is e to the power 2 beta j star plus, and then it is plus 2 beta delta n. So I linearize and write 1 plus 2 beta delta n plus 1. Right? So that's the right hand side. So linearizing in delta, it is e to the power 2 beta j star plus this, and then the left hand side, which is this cos hyperbolic 2 beta j star plus the derivative. So it is 2 beta sine hyperbolic 2 beta j star times delta, right? Delta n. So Taylor expand. So I'm Taylor expanding this about j star. So it is the right. So that's the. And cos hyperbolic 2b j star is the e to the power 2 beta j star. So this cancels with this over here. and then it is 2 beta e to the power 2 beta j star, and then it is delta n plus 1 is 2 beta, and it is sine hyperbolic 2 beta j star times delta n. So this is 2 beta and j star in the fixed point is 2 beta j star is equal to 1, right? That was the, that's what it was, right? The fixed point was e. Yeah, so e to the power 2 beta j star equal to 1 was the fixed point. So this is 1, and you have delta n plus 1 is equal to 2, and then it is sine hyperbolic 2 beta j star, which is sine j star. The thing was the fixed point was e to the power 2 e to the power 2 beta j star is equal to cos hyperbolic 2 beta j star. So sine hyperbolic 2 beta j star is so this is this one, the fixed point value is j star equal to 0. So cos hyperbolic 2 beta j star is very close to 1. So this has to be very close to your that is, I can linearize. That is what I'm trying to say. That this would be 2 beta j star times delta n. I mean, cos hyperbolic 2 beta j star is close to unity. So sine hyperbolic 2 beta j star should be close to 0. J star is small. So this is delta n plus 1 is very nearly 2 beta cancels over here, something which is positive times delta n. Huh. What is 0? Yes, right. All right. Very good. J star being technically, I mean, cos hyperbolic 2 beta at this is, I mean, this asks for work on your part. Technically, delta n plus 1 is 0. So this is, I mean, and therefore you don't pick up any contribution over here. If I set this equal to 0, it is just not what you are getting, neither stable nor unstable, just not moving, right? So at the linear order, it is just not moving, which means I have to calculate the next order. So that obviously, I mean, since you asked for it, I mean, it's an assignment that calculate the next order. Delta n square could, I mean, the first non-vanishing, I think it's delta n square doesn't vanish. But yes, right, at the fixed point, the first. Yeah. So things would be, so at the linear, this fixed point, I mean, all the things with this problem are somewhat, the one-dimensional model is a little problematic. That is non-standard, and therefore when you are looking at this high temperature end, there is this fixed point over here. You are going to move away from it, but not exponentially. Normally, I mean, one moves away exponentially from a fixed point over here. You are not going to move away. So, I mean, you get, but sort of, you get the idea that this is going to, I mean, it's a positive term. It's going to. What? Yeah. 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 J star equal to 0 is an unstable fixed point. No, but yeah, it corresponds to, but now you have this, yeah, absolutely. So J, uh, yeah. The point is that that is what where it goes is a tricklish issue, because in one case over here it is actually linearly unstable. I mean, that is, if I were to do the calculation around J star equal to infinity, you would find that you are linearly unstable and life is all right. Over here, you find that it is linearly stable, linearly nothing, right? So linearly nothing, and now it is, for, as I said, for you to find the sign of this term. I didn't say it's unstable. You see, the point is that I didn't say that it's unstable because, I mean, it technically vanishes. So there is a, I mean, you are right about the question you are asking, that if I start, obviously, if this is linearly unstable over here, I have a fixed point here, I have another fixed point over here. Along a line, they have to alternate. So they have to alternate along this. But here I find, I have not done it yet, but I have found that I will find that I'm saying it's a critical fixed point and therefore it has to be unstable. Over here, what has happened is I'm saying that it is undetermined. Essentially, I can't make a statement. There is this coefficient is technically 0. So there has to be the next one. And that is why, I mean, the point is that I have asked you to, I mean, it's a good homework exercise to actually carry out and see if you get this to be negative or not. So you would find that this is undetermined on the linear spacing. So it's a funny problem where you would find that it is what it means essentially that if you move it away, if you start from here, it will take a long time for it to come back over here. But it is not that it will go heading for this fixed point, which it will. So this, on the other hand, over here, the linear stability analysis is again a bit funny. So over here, at least the linear stability analysis is beta J star equal to 0. And I mean, you know that it's a funny fixed point, and it is going to be locally very slow. All that you know is that this vanishes the time, but then the other one, which is over here, says that cos 2 hyperbolic 2 beta J star, and I do a linear stability around that. The answer is that it is J, so I have to take the derivative with respect to J. So it is 2 beta sine hyperbolic 2 beta J star. So 2 beta sine hyperbolic 2 beta